Diffusion models, it is mainly regarding learning a mapping between an unknown distribution to a known Gaussian distribution. And as such, it's used as a powerful tool for generative modeling. Diffusion model can be described as learning the backwards stochastic differential equation described below, with mu describing the drift coefficient and G describing the diffusion coefficient, where dW is the Wiener process, which is basically adding little Gaussian noise. And for this to be SDE, if I'm not mistaken, the mu should be an affine transformation, and G is defined by the noising schedule. So it's been discovered that this SDE previously has a marginal distribution equivalent ODE formulation described below. And so instead of solving the SDE numerically, oftentimes what people will do is they solve the probability flow ODE numerically instead, as that will allow us to arrive to solutions with essentially less iterations.
Can I ask you a question?
Yes, go ahead.
Okay, so what is the drift coefficient, and what is G, and why could you look at the first equation in the other page and relate that with the equation that is shown in the following page?
So this is right. So this is proven, I think, in a paper called Score Matching Generative Modeling something something. There is a paper called that, and in that paper they relate the SDE to ODE, right? They prove that the marginal distribution PET of x generated by the SDE is equivalent to the marginal distribution generated by the ODE.
Okay, so that's, can you say that a little bit more? I mean,
right.
What's the difference? Okay, so the SDE is a stochastic differential equation where the coefficients are probability, and ODE is, the coefficients are deterministic, right?
Yeah, in the ODE, the coefficients are deterministic, but the initial condition is sampled from a Gaussian. The initial condition in the ODE, the initial conditions are sampled from a Gaussian, so there is still a marginal distribution.
The initial condition is separate from the Gaussian? What do you mean by?
No, it's sampled from the Gaussian.
What?
The initial conditions are sampled from the Gaussian. Right. So I can quickly show you the proof right here to describe what I mean. Give me a moment. This is score-based generative handling. Yes. Blah 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 blah. Okay. Right.
So mu, sorry, just interrupt. Mu is.
So in this formulation, mu is fxt, and the gxt would be, because there are many papers and different papers use different notation, but essentially in this paper, fxt is the mu, and gt is gxt.
I see. So it's exactly 1-to-1.
Yeah, exactly. So this is the paper that shows the relationship between the two. And so what they start off with is, they start off with this SDE, general form SDE, right? And the marginal distribution of this SDE follows this equation here, right?
Okay, now, so SDE is where the coefficients are random variables, right?
No, SDE is stochastic differential equation, and what that means is the solving process is stochastic. So stochastic differential equations tend to be like this. So the forward process is stochastic, and the diffusion model is trying to learn the backwards process, which is also stochastic. And so we go from noise to data in a stochastic manner, where because the SDE has a dW term here, and that dW term here is from the Gaussian distribution. So it is deterministic dt plus some noise value, little bit, continuously.
Oh, so the G, did you say G is is probabilistic?
The G function here?
Yeah.
No, the stochasticity comes from the dW.
dW is stochastic.
Yes, dW is, I can't remember. Normal distribution of mean 0 and the variance is square root t, I think. I'm not sure on this. I can't remember off the top of my head. But essentially the randomness of this ODE, this SDE comes from the dW term.
Okay, so you got a deterministic term and a
Yes,
stochastic.
Exactly. So this is a deterministic portion and this is the stochastic portion. So you can, there is many ways to view it, but one way as well is to view it as taking a step back from the point, stochastically adding noise, and then taking a forward step. That's how the EDM paper likes to view SDEs. But the randomness comes from here, and that's why the noising process is also jumpy, because this is the SDE.
Okay. Okay, so it's SDE, and you're trying to relate it to ODE.
Yeah, because basically SDE is it's good, but what happens is because it's so noisy. Let's say it's a continuous equation, right? And we are trying to discretize it. And for SDEs, when you start to discretize it, essentially what happens is you don't get good sampling, because the solving process from noise to to data is stochastic, right? And so they want to relate it from SDE to the ODE here. You see these deterministic lines? So if you can relate it to SDE to ODE, then you can solve using an ODE. And ODE, since it's deterministic, is more well controlled in some sense, and then that allows you to use less samples.
Okay, so we have to keep in mind that we're going from SDE, stochastic differential equation,
to ordinary differential equation. But they are marginal distribution equivalent, so they will generate the same distribution.
Okay.
Yes. And the bottom part I showed is basically the proof. And the proof essentially goes along the lines of proving that the marginal distribution T of x here, this is for the SDE. And for that ODE I showed, they proved that the PDE, partial differential equation describing the marginal distribution, is equivalent. They are described by the same partial differential equation, and therefore the marginal distribution is equivalent. If that makes sense.
Okay. Okay.
So the bottom line is that they have the same marginal distribution, and therefore solving this ODE will get the same distribution as solving the SDE. So they solve the ODE instead. Yeah.
So at least the same solution, but SDE.
Different solution, but same distribution.
Because it's jumpy, it's not smooth.
Yes.
It's difficult to work with, so
yes.
People work with ODE.
It's more preferred, yes.
Okay.
But the solutions are different, but the distribution is the same. Distribution equivalent, not solution equivalent.
Okay, distribution of what?
The marginal distribution, PATX.
Okay.
So if I would take the distribution generated by the SDE, and I would take the distribution generated by the ODE, and at every time step, if I would slice it and I compute the distribution at this time step, it would be the same. They would generate the same distribution. Okay.
Oh, I have a question.
Yes.
So you call it ordinary differential equation, right?
Yes.
But here in the equation, I see two variables. The first is the t.
Yeah,
and
no,
the second is the w.
This is a partial differential equation.
Yeah, that is
the partial differential equation is of the marginal distribution. The ordinary differential equation is describing the denoising process.
So it doesn't clear. What do you mean? What did you say?
So this is to prove that the ODE is equivalent, but this is the PDE describing the marginal distribution. So the ODE is described like this. This is the ODE. So it's respect to only one variable dx over dt.
Ah.
So this is the ODE that we'll use to solve. But to prove that this is equivalent to this thing here, they prove it using the marginal distribution PT of x. And PT of x is a function of t and x, so it's a partial differential equation essentially. They use a partial differential equation to prove that these two equations are equivalent, but we use the ODE to solve it in a way. If that makes sense.
Makes sense.
Okay. Okay. Okay, so anyways, there's an ODE system, and essentially, neural networks, what they do is they approximate this function gradient log PT of x, right? And they do this x0 prediction, epsilon prediction, and epsilon and x0 prediction. What they do is the gradient of log PT of x, since each PT of x is a Gaussian distribution, the log PT can be obtained from the epsilon prediction, x0 prediction. Anyways.
Sorry,
yeah.
I can recommend a little bit so that you present a little bit slower, because too fast every people cannot capture the idea.
Okay, no problem. Up to here is clear? Right, for more clarity actually, here this paper has more description. So this is under the x0 prediction model. So here is the score matching that I mentioned below, before. And this is x0 prediction that predicts the x0 of a model. And so we can use this, where this is the model output, to obtain the score, to approximate the score function after training x0 prediction.
X0 prediction.
Yeah, x0 prediction essentially gives, the loss can be viewed as giving a noisy image. Here. So y plus n is a noisy image, so giving the model a noisy image and predicting the clean image. So predicting x0.
I would complement this. So in ordinary differential equation,
Yes.
when you try to solve the ODE system,
Yes.
you want to find a function that map a initial condition into the function, right? With respect to time, right?
That has to do with inference, but for training, there's nothing to do with that for now.
Yeah, I mean that you have to explain that so that people can capture
Right.
what the training process trying to find.
Right.
Right.
So the training process for this is to learn the x0 model, which is this model, and so that we can essentially approximate the score function. The goal of diffusion is to approximate the score function. This is the score function.
Cannot understand when you map.
So the idea is this, right? So we know that data has this ODE system here, and we know this function here, we know this function here. We do not know this function here. This is a question mark. So we approximate this by a model, and that's the diffusion model.
Oh, so now you are explaining that the differential equation is not. We don't have the differential equation yet.
We don't have it yet. We know it looks like this, but we don't have this function here. The score function we do not know.
So even though you try to find the ordinary differential equation,
yes,
you didn't know the formulation yet.
Yes.
So now the first step, you try to find the formulation of the
score function. Yes.
The score function.
So how diffusion models train is they train like this, and once after training they can use this function to approximate the score function. Okay. So that's diffusion.
But now, follow your presentation, I didn't understand the intuition why the score function.
Why the score function?
Why the score function? You find the score function by doing that optimization.
X0 prediction. Right. That has to do with a lot of things, but essentially, the short story is that we know that the P of x of theta, sigma, follows a normal distribution given by, where is it? Anyways, it follows a normal distribution centered at x0, like this. P of x sigma follows a normal distribution of x0 and sigma t squared, I think.
Sigma is a hyperparameter. Is that
Yeah,
correct?
sigma is the noising, how much you add noise at every time interval, t. I. So we essentially know the marginal distribution, conditional marginal distribution, on given the sample data.
Given a sample data.
Yes.
Given.
I think it's better to explain from the DPM to the SDE.
No, but DDPM explains differently. We talk about Markov chains
Yeah.
and KL divergence. If you want to explain from Markov chains or KL divergence, it's a bit weird. Go to back to like continuous things.
That is more people can imagine
Yeah.
how it is look like.
Yeah, you have.
You want to explain DDPM?
Please.
Yeah.
Oh, but that's very big.
No. From score based the paper.
From score base? Okay,
From
okay,
the
yeah. Oh,
Appendix.
right.
Appendix.
I can explain this. Okay.
Yes. That will be more concrete.
Yeah. So essentially, we do this. Essentially, and this thing conditional on sample x0. So xt is the image, noisy image xt, given the clean image, right? And so we learn the score matching of xt to match the score function of log p of xt given x0. And strangely enough, at the minimum point, you will xt of
Sorry. I would ask you that about the ODE function.
Yes.
So, what is the initial condition and what is the final image that the ODE generated?
Well,
Is that the noise at the initial condition, and
noise-
is that the target is the clean image?
yes.
And why we given the clean image here? Here you mean that the S0 is the clean image, right?
Yes. Right.
Why-
So actually,
you invert the process or some?
no.
Yeah.
So score matching. Normally, what we actually want to do is match the score function to gradient of log p of xt, not given x0, right? But we cannot really sample from that.
But
So-
what does it mean to doing that?
Hmm?
What does it mean to doing that function?
This function? What do you mean?
Your explanation, I doesn't feel that given a clean image. What does that function try to find?
14. This paper 14.
You want to explain from 14? What 14?
You go to 14. Yeah. Scroll up.
You want to go from here.
From 22. 22. Equation 22.
22.
Yes.
You want to go from here?
Yeah. This is more easy to understand.
Okay. Oh, but this one just talks about describing to SDEs, no?
Yeah. From SDE we can get ODE and we can talk something from ODE.
Okay. No, but they understand ODE already. Do they understand ODE? They understand ODE?
No.
You understand ODE?
All the version here, I think that they have the
You understand
the
ODE?
knowledge about ODA and also the BDA,
But they don't know what is
and
ODE.
you have to explain the mapping between them.
Okay. So anyways, this is just short sidetrack, but this is just the DDPM sampling procedure, and they how they connect DDPM to SDEs in the first place is they divide it by n, and essentially what happens is what do they do again? I can't remember the proof. Okay, yeah, they divide by n times n here, and then what they do here.
Okay, so actually equation 22 is just the presentation figure. Can you go to the presentation slide?
When you go 22, 22 is about variance exploding though.
Yeah.
You want to explain variance exploding?
Explain what is the SDE.
SDE. They know SDEs already. You know SDE very well.
We don't know SDA, we should know the BDE or ODA. So what is that SDA and how? I mean that we don't care about the equations. We just care about the like the meaning of them and how to map between them.
Okay, okay. So anyways, first let's start with the forward SDE, right?
Yeah.
So, oh boy. So there is a forward SDE described by this, right? For now, let's ignore what FXT and GT is first.
Yeah.
They will be described later. But essentially, this is the forward SDE going from data to noise, right?
Okay.
And then, I think it's Anderson. Anderson proved that there is a reverse SDE. Yeah, Anderson 1982. Described by
So
this.
you mean SDE is the process from
Process,
the clean
process.
image, from the clean image to the noise.
Yes, from clean image to noise, there is a stochastic process described like this. This is the noising process, right? And there is a reverse going from noise to clean image, described like this.
This right like that.
Yeah, this is the counterpart to the. This
So
one.
they prove that
This is Anderson.
there exists inverse mapping process
Yes, reverse
corresponding
stochastic
to
process.
that function.
Yes, according to this function, right? So there's a stochastic process going from any distribution to noise, and then there is a reverse process going from the noise to the clean, described by this function.
Okay.
And essentially-
and what is S here?
Hmm?
S here is the distribution of data.
Where's S?
S.
X.
The S. You mean the S
X,
here?
X is the image pixels.
Image pixel. Okay.
Yeah. So this is how basically showing how the image pixels move across time, X to T.
And what is W here?
W is a Gaussian distribution. So this is deterministic, dx over dt. This is deterministic, plus a little bit of Gaussian distribution, dw. So the randomness of this, you see, this is a random process, stochastic process, comes from the dw.
And W here is a multivariate
Multivariate Gaussian distribution, yes.
Gaussian distribution, right?
Yes.
And the sign of the W is the same with the sign of the S.
So, yes. Yes.
And it's a function, random function.
You sample from this Gaussian. So normally,
It's a function of T. No?
no. This is just Gaussian distribution, noise, and then scaled by GT. So I would at every sampling step going backwards.
But you have some D here, dW here.
Yeah.
D what? D
dw is dw is what again? It's normal
is
distribution.
over the
dw is normal
is
distribution.
from 0 to
Yeah.
n or what?
Where is it?
24.
24. Did you say?
24 to 25.
Yeah. Oh, yeah, right. dw is square root of delta t times the normal distribution, zero mean normal distribution.
Square of T.
Yeah, square root of delta
multiply.
t times normal distribution 0i.
Normal distribution. So it's a function of T. It is essentially the function of T.
Yes, it's square root delta t.
And times noise. Noise.
Yes.
Okay, so that makes sense.
Anyways, there's this function, and essentially we don't know this, so we cannot just do that. We don't know the score function.
We don't know. Okay.
This is something we don't know, so we need to approximate, right? And instead of, because we cannot sample this, we don't know this, so we cannot really score match this. Instead, what we do is we score match gradient of log of p of xt given x0.
Okay.
Yes.
You,
so
so
we wanna
I
learn-
want
we
to
wanna
ask
learn
that.
this.
I want to ask that that function is a function of S. Okay.
yeah, it's a function of x, the pixel thing.
So given a target image,
No, given a noisy image x, how to go to the gradient? What's your next gradient direction? So I'm trying to go from noise to clean, right? And then at any arbitrary time step here, let's say I'm here, I need to compute the gradient to tell me where to step, so that I can go more towards the noise, the clean.
So you given the clean x0 here.
No. This is the gradient of xt given x0.
Yeah, what is x0?
X0 is the clean, yes.
Clean limit, right? Given
Yeah.
the clean limit,
Yes.
you try to find.
No, this
Yeah.
is the model. You're matching this.
Right, I understand that. That's the model, and the term derivative of the log here is the label for that model, right?
Yes.
And how can you find the label for that model?
Can you find the label?
So here you have a model here, right? Parameterized by the theta,
Yes.
and here is essentially the label of this model.
Yes.
The label
Trying to
of
match-
this model.
Trying to match it to that, yes.
You try to match it into this, and
It's
you
not label,
say
it's
to
more
me that
regression.
you said to me that this is unknown.
Yeah, you cannot do. Yeah.
Unknown.
Yes.
This is unknown. And how can you fit unknown into the
No,
model?
so-
You have to explain.
Right. So they match like this, right? And strangely enough, at the minimum point, this will equal to this. The minimum point minimizing this will also will cause xt to be equal to this.
Explain the intuition behind that.
They don't explain it in this paper, so I can't remember what did we do again. What was it again?
Explain the intuition. How can we solve this optimization problem, and then we have a model of that gradient.
Yeah, how was it again? Do you remember? I can't remember. It's in one of those old papers. Oh right, was it an MIT paper? This paper referenced another paper, I can't remember.
No, we don't need to prove that.
Yeah, we shouldn't prove that. Anyways,
you shouldn't.
it's just a proving.
13.9.
Okay, so explain the optimization process here, because that's a lot of expectation going there, right? Then I mean that optimization objective.
Oh, this is just sampling x0, and then from x0 we get xt, because we know the noising process to xt, no? And from here we get xt, we just compute this. And xt given x0, we know the distribution is Gaussian. Xt given x0 is normal Gaussian, centered at x0 with mean sigma t squared I, right? And since we know that, then we know this distribution. So we know this distribution pt of xt given x0, so we can know the log of this, and then we can know the gradient of this.
I would ask that, do you know the forward mapping? Do we have the forward mapping of the generating noise process?
What do you mean by forward mapping?
I mean that given a clean limit, do you know that the forward mapping, the
Yes.
exact forward mapping of?
Yes, because if we remember correctly, the forward mapping is mapped by this function.
So we
This
know
is
that,
known,
right?
F and G is known.
We know that, right?
Yeah, we know the forward, we don't know the reverse. And we're
Uh,
trying to learn the reverse. And they learn it, to learn the reverse, you need to know pt of x. And essentially, instead of doing pt of x, you do p of xt given x0. And the reason why we do this is because given enough points, at the minimum point, the score matching function will be equivalent to pt of x. So you're kind of indirectly learning pt of x,
I
essentially.
see here, this is B0. This is not
Yeah, because
unknown.
this is-
known.
Yeah, this is given xt given x0, the distribution of xt given x0.
But this is known, right?
This is known. This is unknown. By matching with a known distribution, you can learn the unknown.
Okay, so this is known.
Yes.
This is known, and we can calculate the label. We
It's a
calculate the label
regression.
for
It's not classification. It's not a label. It's like a regression.
I mean it's the same.
Yeah.
But we know this label.
Yes.
We know this label and we try to fit it into this model.
Yes, exactly. And the minimum point, S star of this minimization objective will cause it to approximate this.
So it makes sense. So
because the intuition is we're doing this expectation over all the x zeros, and expecting it out, you will get this.
oh, so it makes sense. Do you have any question, Professor?
No, I don't.
Okay, that much.
Okay. Anyways, so diffusion models learn by score matching, right? They approximate this, and once you approximate this, you can actually essentially model the ODE system. Okay, and that's where the iterative process comes in, is solving this ODE system. Okay, sidetrack. Physics-informed neural networks, right? And what they are scientific machine learning technique, where you can essentially, so given this equations, by minimizing the residual loss, you can learn a model, x theta t, that models this solution to this system. So essentially, let's say I have a model x theta t, right? If I'm able to compute this, and once I minimize this, once this goes to 0, essentially what this means is x theta t will be a solution to this ODE system, right?
So you are explaining about how to solve an ODE system.
Yes, arbitrary ODE systems using neural approximation theorem of neural networks that are able to approximate any function, and therefore can approximate this function. Yes. Okay. With that in mind, since diffusion models are ODE systems, can be represented by this ODE system, and also since diffusion models are Lipschitz continuous, essentially they have a unique trajectory function, xn of t, right? Where n is the initial condition and t is the time at arbitrary time t. And so using a pin-like approach, what you can do is you can minimize the residual loss between the new parameter theta and the ODE system parameterized by phi of the score matching function. And by reducing this, you essentially are able to learn a model that matches the ODE system and therefore is a solution to this trajectory.
I get lost here.
Okay.
Yeah.
So there are trajectories, right? So you can think of this as trajectories, right? So let's say the trajectory is described by this dx over dt with this initial condition. What pins can do is they can take this x, instead of being just x, they can parameterize x by theta and reduce this loss. And by reducing this loss, x theta t can be a solution to this this ODE system and therefore be a model of the trajectory. So you can model trajectories by reducing the residual loss.
And model the S by theta.
Does that make sense?
Model the S. What do you mean by model the S by theta?
As in, you have a model that takes in t and outputs x. So then the model is a model of x.
S is variable, right? And essentially this is
Yes.
the already the theta. S
Yes.
is already the theta.
No, x is not really theta, no.
S is variable, right?
The randomness of x comes from its initial condition. Because the ODE system is deterministic, so the step forward process is deterministic now, right? And the backwards process is deterministic. The randomness all comes from the initial condition. The sampling.
Here. Let I explain to you. So ODE system, right?
Yes.
Here is the D. For
Yes.
example, for example, just given only univariate.
Yes. Single variable.
Here the S, right? Given some initial condition, mean that the initial condition of the S,
Yes.
we have different initial condition of S, right?
Yes.
And here is the attempt N. at time n, right? The final time state.
At time t.
Time
this
t
case.
in this case.
Yes.
We have ODA is essentially different stochastic process. Map to this, and we want
We
to find
have moved away from stochastic processes. We are now all deterministic now.
ODA.
Because ODA is deterministic.
ODA is deterministic, but there is a mapping. There is a mapping between here and here.
So
right?
for now,
there is a mapping between here and here.
Yes.
There is a mapping between here and here.
yeah,
Right.
non-intersecting mapping because the solutions are unique, but mappings. Yes.
Non-inter.
Yeah, the mappings are non-intersecting. The
Maybe
solutions
intersect,
cannot intersect.
Oh, cannot intersect.
But anyways, that's
But
not
anyway,
important.
that's not important. So go in here,
Yeah.
and you say that
So this is the solution, right? Like
this is the solution. This
Yes.
is the solution that we.
yeah. So this is the solution to the ODE system represented in here. Let's say, right? But this thing is cannot be really seen unless you solve the ODE by hand.
Right.
Right? What we do is you can do iterative sampling, and another way instead of iterative sampling is you can use a model, and you can use your model and model this unknown function. So let's say you have initial condition here, and you go in here, right? So that's the solution to the ODE system, right? And this is not observed, and instead of modeling it, what you can do, how you model it is you can use a neural network, X or T, let's say in this case, and by reducing the residual loss, you can model this unknown solution.
If I model this, I will model this is the f of theta t, and if I have another condition, initial condition, I would model it as some initial condition.
If there's another initial condition, it's not an OD.
Why don't we model like this? And what is your model? What is your model? What is your way of model? If I gonna model this one, I will use a function
Yes.
with the input of t.
No, this
and
is just
also
a
the
review
initial
of
condition.
pins. This is a review of pins.
Yeah, but how do we model this?
So now we need an initial condition, right? So in pins normally, let's say for this thing, we only model the t, right? So we have x of theta t models this thing, and arbitrarily, if we want to model for arbitrary initial condition, this for particular initial condition.
But I don't even understand about this. What is the way that you model the function? What is the way you model the function? I don't understand it.
What do you mean? What's the way you model the function?
You say to me about the model, right? The modeling, right?
Yes.
What is exactly the modeling here?
You're trying to model the trajectory here.
But
So-
how you model? I didn't see how you model that.
You reduce this loss, you will automatically model the function. So this is a way to indirectly model the function.
I mean that. What is theta here? I don't understand.
Theta is the neural network used to model the x.
Anyone can understand that? Can explain a little bit better?
So the x in here, we can imagine a solution for that ODE system, which is something
I imagine everything
x
there.
equals to.
Can you map into that?
Okay.
Could you explain the loss function?
The loss function here?
Yeah. X theta.
Maybe.
Okay. So simple case, right? So given an initial condition k, let's say L, right? Let's say the OD system dx over dt is equal to k, right? And this one we know is a linear equation, right? So we know the true f. Let's say, but the true f is unknown, right? F of t. Let's say here's t. This is f of x, f of t, right? And this is the true f of t, right? It's a linear function like this, right? And initial condition is at 0. Let's say at time t equals 0 is at 0. So this is the initial condition I set, right? And I want to learn this solution without actually seeing the solution,
Okay.
right? So, like instead of doing regression by, like let's say I have a model. So the naive way is you have a x instead of let's do f theta t, right? And naive way is you would do f theta t minus ft, right? The mean square between this, right? If I know the function, I would just do the mean square between them, right? But now, remember the solution is unknown. I cannot actually see the solution, so I don't have access to this, right? So to indirectly learn the solution, what you can do instead is you take the gradients df of dt with respect to the input, right? And if the gradient of with respect to this input t is reduced like this, so at the point here, if this is 0, essentially what this means is df over dt is equal to k, right? And you realize that what happens is now your function satisfies this ODE system. So your function is now a solution to this ODE.
Okay.
So this is how you can indirectly solve any arbitrary ODE system by minimizing this loss. So I don't have to see the unknown function. So the trajectory can be arbitrarily complex, and instead of solving it, I can just do this, and by minimizing it, once it reaches 0, essentially you'll become a solution to this. Does that make sense?
Makes sense. Good explanation. Okay.
Okay. Anyways, going back to diffusion, so we know that the diffusion model can represent the ODE system, right? And we know that we can use pins to reduce the residual loss and learn ODE systems, right? So the question is, can we use pins to learn this diffusion ODE systems and therefore generate images, right? In a pin-like approach. So physics-informed distillation, essentially, right? Okay. So there is an unknown trajectory function xn of t, right? So the trajectory function depends on the initial condition and the time t, right? And we want to learn this unknown equation that is a solution to these ODEs, essentially. And so what we do is, similar to how you would minimize this, you would just minimize the now x theta, the x function here, we replace it with a model, right? So x theta n of t, right? And this model, we reduce the loss between this and the residual loss, similar to how you do pins. So the loss can be looked at as matching here, right? X theta n t, we reduce that loss, similar to how you do in pins, right? And to learn to solve ODE systems, two things are needed. One is to solve the differential equation, and second is you need to solve the initial condition, right? And to solve the initial condition, what we do is we use skip connections. So because for initial condition at time t, right, the value has to be equal to the initial condition, right? So ft equals to, let's say, n0 or something like that, right? So you have to satisfy that initial condition. And what we do is we set the c skip at time t to be equal to 1, so that at time t this thing is n, and then this is 0.
Oh, how do we need to solve? What do you mean by solving the initial condition?
When we solve ODE systems, let's say here, right? Remember, I set the initial condition to be equal to 0, right? So when I integrate, so let's say I integrate by hand. Where's my hand? Right. So let's say go back to this example here, right? So if it's like this, then if I integrate, right, k dt, right, this will equal to k plus c. And I solve this c by satisfying my initial condition f of 0 equals to 0, right? That implies that, this implies that c will equal to 0, right? So there is a, when I integrate, there is a initial condition that's, I need to satisfy this initial condition, right?
But is the initial condition already embedded in the function that you mentioned before, right? S,
yes.
C, and N, right? N
Yes.
is already in the function. What
Yeah,
do
so
you
how
need?
we do it is, instead, there's two ways to do it, right?
Ah.
You can either learn to satisfy your boundary condition, or you can create a function that automatically satisfies these boundary conditions. And that's what we do here, is we set it so that the skip connection at time t will be equal to 1, and the out connection at time t will be equal to 0. That way, the neural network output is zeroed out, and it's just n. So you will satisfy your initial condition always. So we don't have to learn the initial condition. Does that make sense?
Well, I cannot capture that.
We have an initial condition here, right? So for this model, right? This model is a solution to this ODE system only if it satisfies this ODE system, which means the loss is 0, and this model is equal to F0 equals to 0, satisfies the initial condition. You have two conditions so that you can be classified as a solution. You need to satisfy the ODE system and the initial condition. And you have to learn this too, right? But we don't want to learn initial condition, so we just choose skip connections so that this initial conditions, these boundary conditions are already learned for free.
There is a way to learn that, okay?
Yeah, so you can learn them without learning them.
Okay.
Okay. Now, numerical differentiation. So remember the loss is described like this, but instead of doing it, what we do is we do numerical differentiation because if you can see here, it's with respect to dt. So it's a single variable, so numerical differentiation is not a big deal. Right?
Numerical differentiation. Okay.
And the reason why is because to get dx over dt, what you need to do is do forward mode backpropagation, and then you backprop on your forward mode backpropagation, which can be expensive.
Wait. Here you say that using the for loop for forward like this one, numerical differentiation is not computational cost high. The cost for doing that is not high.
Yeah, not as high as well, actually can be similar depending if you do symbolic differentiation, but yeah, it's just an easier way to do to approximate the gradients instead of the forward mode propagation. Anyways, we approximate it with numerical differentiation for easy because forward mode is not always available on all packages. This is just a simpler way to do it. And also the error introduced by forward mode is bounded.
Bounded.
Yeah, we proved that it's bounded, so it's not that uncontrolled, right? There's a bound to this error. Numerical. So dx over dt, we replace it to numerical differentiation. And it can be described like this. Okay. So, right, the loss can be described like this, which is just matching the gradients with replacing the differential dx over dt with numerical, right? And so experimental results, we show that the teacher model representing the OD system and the student model for the same noise produce the same image, essentially showing that they learn well. And the trajectory functions, remember we are mapping the trajectory, right? So here's the trajectory of the teacher, here's the trajectory of the student, and we see that at all time steps t, they are the same, showing that they learn well as well, the trajectories. And I think that's the end. Yeah. Okay.
Okay, thank you for the nice presentation. So, you said further questions. If you're in the Zoom, please turn on the mic, and if you are online, you can raise your hands.
So I have one question.
Yes.
So overall,
Yeah.
you say the presentation say that if we try to estimate the gradient or gradient and we use some numerical method for forward the process, generating process, we can save computational cost of as opposed to the
Forward mode backpropagation.
forward backward
Yes.
propagation of the conventional way of
No.
diffusion.
Forward mode backpropagation is not conventional way of backpropagation.
I mean conventional way of diffusion generating
No,
process.
the conventional way of diffusion is to solve it iteratively. So this trajectory is solved iteratively using Euler rule or so on. What we do is we model the trajectories instead of solving it iteratively. We model it with a neural network. So the neural network solves it, right? And so once we train a neural network to solve this ODE, we can essentially solve it in one step, because we just input the noise and the time, and then it knows the solution.
But you have to do a for loop, right?
No, there's no for.
You learn a function over time.
Yeah, but then
in
when you want
condition.
a function over time, and if I want to get the clean, I just put in the n prime and I put in 0.
And you do some numerical differential equation.
Numerical is during training. Because remember the loss has dx over dt. So I replace this here with the numerical.
So after you find in the gradient.
I approximate the gradients with numerical differentiation
Okay.
in the loss. But after training, it can model this ODE, and so sampling is just n and at 0, right?
Okay.
And then you get data.
Yeah, understand.
Okay.
Is there any other questions? For those in online, do you have any questions? If not, let's give him a big applause for the nice presentation. And thank you for coming today, and you can take a snack up when you go out.
Okay.
See you next week.
See you next week. Thank you for your presentation. I asked a lot of questions, but anyway, I made